I'll be talking primarily about a paper that came out, well, really a pair of papers, one that's about a year and a half old, and another that came out over the summer. There's another very important reference for what I'll be talking about today, which is also a very nice paper by Tom Hartman and friends, which came out at the same time as my first paper with Witten, which also articulated many of these ideas. But I think really in the spirit of an informal workshop, what I'd really like to do is try and keep this as interactive and as informal as possible. So I will talk about a few technical details, and I've chosen specifically some technical details to discuss that I think might be of particular interest to people there at the workshop. But I also want to really focus on some of the more general ideas, some of the more general concepts. And so because of that, I'm also going to be introducing a lot of open questions, hopefully as a way really to spark discussion and to spark some kind of interaction. I will say just the one thing is that I can't hear you guys terribly well. So I do encourage people to interrupt and ask questions. And moreover, I encourage you to do so loudly so that I can hear you. Great. And by the way, is this nominally a 45-minute or 60-minute or something like that? Is there
60 minutes?
What was that?
60.
60. Okay, great. Good. I suspect I may not take that long, so please interrupt and ask questions or make comments. So let me just begin with a very general overview of the mystery that I'm going to be trying to think about today. So when we think about the ADS-CFT correspondence, we usually think about it as an equivalence of quantum theories. That is to say, you think about ADS gravity as a quantum system, and quantum gravity in ADS should have a Hilbert space, and it should have a Hamiltonian. And that Hilbert space and Hamiltonian should match the Hilbert space and Hamiltonian of some conformal field theory. And of course, there are all sorts of other observables, correlation functions, and so forth that should match. And we usually think of this as an exact equivalence between quantum theories. But it was observed, and I at least learned about this first from a very nice paper of Maldacena and Maus, which came out in around 2005 or so. It was observed that this correspondence is really in quite a bit of tension with the existence of a certain class of solutions of general relativity or of theories of gravity in Euclidean signature, which are known as Euclidean wormholes. So what is a Euclidean wormhole? A Euclidean wormhole is a solution to the equations of motion, or perhaps more generally, some kind of configuration that would contribute to a Euclidean signature gravity path integral, which has the property that it has two disconnected boundaries. So here I've drawn a cartoon of a Euclidean wormhole. So this is some Euclidean geometry with two boundaries that I've called sigma 1 and sigma 2 that are connected by some geometry in the interior. And I've drawn this particular geometry. So it has a two-dimensional boundary, which is a pair of Riemann surfaces connected by a three-dimensional bulk, because that's the sort of prototypical and simplest to understand Euclidean wormhole of this type. You can write down an exact metric. You can study it in a great deal of detail. But even without studying it in detail, it apparently leads to a contradiction with our idea that ADS-CFT is an exact equivalence between quantum theories. And why is that? Well, it's because any solution to the equations of motion should contribute to the partition function of the theory. And in particular, the existence of such solutions would seem to give a contribution to the partition function of our gravitational theory in the presence of two disconnected boundaries. And in particular, because it's a connected solution, it's not going to factorize. So it won't take the form of a product of two separate functions of the data on the Riemann surfaces sigma 1 and sigma 2, respectively. Whereas if you think about conformal field theories, in Euclidean signature, it's practically part of the definition of a conformal field theory or a quantum field theory that the partition function on two separate Euclidean surfaces, Euclidean geometries, should factorize. And this seems to be a pretty serious problem for our understanding of holography as an equivalence between two quantum mechanical theories. Now at the time that this Maldacena and Mao's paper was written, I think there were really two potential resolutions to this question that were contemplated. Well, perhaps I should say three. One possible resolution was that wormholes don't contribute for some reason. So, for example, perhaps we don't exactly understand the path integral of quantum gravity in Euclidean signature. Such a path integral is presumably an integral over some fancy contour through the space of metrics, through the space of geometries. Maybe there's some reason why the Euclidean wormhole solutions don't live on that contour of integration for the gravitational path integral. But we didn't really understand at that time, nor do I think we understand now why that would be the case. A second possibility is that these wormholes do contribute to the path integral, but there are other contributions that will cancel them out for some reason. In particular, there are some other contributions that will restore factorization to the path integral of quantum gravity when you have disconnected surfaces. And I think nowadays we understand a bit better how that might happen. And of course, a third possibility that I think I probably should have added here is that ADS-CFT is wrong. Okay, always a logical, if I think unlikely possibility. So this is really the thinking, I think, at the time, 15 years ago or so when the paper was originally written. But nowadays, I think in the last couple of years, really, a different interpretation of this puzzle has been presented, which is the idea that perhaps they do contribute and we should take them seriously. And then think of ADS-CFT as a sort of more generalized relationship between gravity and conformal field theories, where instead of a particular theory of gravity being dual to a particular conformal field theory, it might be that there are some theories of gravity which are equivalent not to a single conformal field theory, but rather to an ensemble of conformal field theories. And what do I mean by that? I really mean an ensemble in the sense of probability theory, namely that there is some probability distribution over the space of conformal field theories. And when we compute something in the gravity side, that then is interpreted as an average over the space of conformal field theories with this probability distribution. So with this interpretation, we now have an interpretation for this two-boundary wormhole, for example, which is that it's computing something like the variance of a CFT partition function computed with this particular probability distribution. And then the existence of Euclidean wormholes does not mean that ADS-CFT doesn't make sense. It just means that we're studying an ensemble with non-trivial variance. Okay. And this picture would incorporate all of the examples of ADS-CFT that we know and love, things like n equals 4 Yang-Mills theory. Those would just be examples of ADS-CFT with a probability distribution as trivial. It's just a delta function. So that then begs the question of when should gravity be dual to an average over many conformal field theories, and when should it be dual to a specific conformal field theory? And the general picture that I think is probably the consensus opinion, although people should feel free to disagree with me if they have strong feelings about it, is that there are certain simple theories of gravity. Here, I mean theories of gravity like general relativity that are probabilistic. And the characteristic feature of such quote unquote simple theories of gravity is that they are the theories that are simple enough that we can study them using Euclidean gravity path integrals.
Okay.
And these, oh, sorry, there's a question. Yes.
Yeah.
Sorry, do you hear the question?
Yes, I can hear you. If you speak up, it's not terribly clear, but I can hear you. Thanks.
Okay. So if we think about ADS-CFT correspondence as string-string duality, when one side we take G string goes to 0 and then the branes decouple, there is such way of thinking. So we have two theories, one in card space, no branes, and another the flat space with bunch of branes, and then we take G string goes to 0 and the branes decouple, and that's a DCFT. Now, in that interpretation, it's a precise string-string duality.
Exactly. Yeah. So that would be an example of the second kind of theory of gravity that I'm talking about on this slide. So, for example, I think the picture that at least I believe is that there are certain simple theories of gravity, things like just general relativity without the additional degrees of freedom of string theory that are probabilistic. And then there are fancy theories of gravity, like the one that you just described. So, for example, you know, the sort of gold standard example of ADS-CFT is a duality between type 2b string theory on ADS5 cross S5, which is equivalent to n equals 4 Yang-Mills theory. Those are exact theories. N equals 4 Yang-Mills theory is a theory. It's not a probability distribution over a space of theories, at least if we work at fixed couplings. And so that is an example of a theory that is not probabilistic. It is dual to some sort of very complicated theory of gravity on the ADS bulk side. And the distinction between these simple and these fancy theories of gravity is that the fancy theories of gravity are actual microscopic theories with a discrete spectrum, with a Hilbert space, with a Hamiltonian. They're legitimate quantum mechanical theories of gravity, but they're so complicated that we can't really compute anything. So, for example, on the bulk side of ADS5 cross S5, you know, type 2b string theory, you can't exactly compute the spectrum of a theory at finite coupling. You can't determine exactly the microscopic level spacings of the black holes or of other gravitational states in the theory. Whereas on the other hand, for the quote unquote simple theories of gravity, these are theories of gravity which have the disadvantage that they don't seem to contain exact microphysics. So, for example, when you compute the gravity path integrals, you don't get a discrete spectrum, but they are systems that we can study exactly. Okay, and in many cases, for simple sorts of theories of gravity, one can do the gravitational path integral more or less exactly and relate that to a precise average over an ensemble of conformal field theories. Okay. Good. Did that sufficiently answer your question? I'm not sure. I actually can't, the way the camera's pointed, I can't actually see you. Maybe you're nodding or shaking your head or shaking your fist at me. I can't quite tell.
That answers the question, as long as these the fancy theories also have description in terms of some string-string duality.
Yeah, well, I don't think we know of you know, I would certainly be open to non-string theory based examples of a quote unquote fancy theory of gravity where we could understand, for example, the black hole microstates exactly. But of course, I don't know of any examples of that. So of course, I agree with you. Great. I'm happy to return to this later on. I mean, I think this this definitely is an important question. So maybe I'll proceed, but I'm happy to return to this.
Thank you.
Great. Thank you. So the questions, yes, please. Oh, hi, Miriam.
Talking about simple gravity theories, but you have to understand them as full-fledged quantum gravity, can't you?
So sorry, I couldn't quite hear you. What am I have to understand?
Theories of gravity that you're trying to refer to, right? You have to fully understand them as full-fledged quantum theories.
Exactly. Exactly. And that's what I'm going to try and describe. Yes. So for example, I won't be satisfied with these simple theories of gravity just to compute classical actions. I want to compute loop corrections. I want to compute all the non-perturbative corrections and so forth. Absolutely. Absolutely. The thing that I think is quite surprising is, and I think the thing that we still don't quite understand why it works, although maybe I'll make some speculations about this at the end, is why in these quote unquote simple theories of gravity can we compute perturbative and non-perturbative effects and get something that looks so close to a conformal field theory? If you take the examples of JT gravity as described by Saad, Schenker, and Stanford, or the examples that I'll be describing today, these are theories that look extraordinarily close to UV complete theories of gravity, in the sense that they're really dual to a conformal field theory, with the only caveat that it's an ensemble of conformal field theories, as opposed to an individual conformal field theory. Okay. So let me get into some of the more details, and we can return to these sorts of questions. So the questions that I'm going to try and be motivated by today are questions like, if we have a simple theory, how close can we get to the exact microphysics of black holes? What sort of features of the black hole spectrum can we probe? And really, although I won't have a precise answer to this, what happens to these wormholes, these Euclidean wormhole contributions, as we dial the probability distribution from some non-trivial probability distribution to just some sort of delta function? The wormhole should disappear, but I don't think we understand precisely how. So I'd like to spend now a little bit of time discussing one specific model of how this might work. And here, I'm just going to give you a one-page summary where I sort of spoil all of the details, tell you the general picture of this averaged holographic duality. And then I'll spend a little bit of time just reviewing in a bit more detail how it works, rather briefly. So what I want to do is I want to think about an ensemble of conformal field theories. And I'm going to take the simplest possible ensemble of theories that I could imagine, which are free boson conformal field theories. Now, in the map between ADS-3 theories of gravity and two-dimensional conformal field theories, the central charge plays the role of the coupling constant. So the usual formula of Brown-Hanot says that the ADS radius in Planck units is equal to the central charge of the theory, which in the case of a bunch of free bosons is the number of bosons. So a semi-classical limit would be one where we have a large number of bosons. Now, the space of free boson conformal field theories is finite dimensional. Why is that? Well, a typical free boson conformal field theory would involve a target space metric. So here, X is my name for a free boson field labeled by an index I that runs from 1 up to n. And the space of free boson conformal field theories is characterized by a pair of coupling constants that I've called Gij and Bij here, which, if you think about them in the language of string worldsheet theory, are the target space metric and B field of these bosons. So these bosons live on a torus, and the space of such free boson conformal field theories is parameterized by the space of target space metrics G and B fields B. Okay. So you could think of G and B as coordinates on the space of conformal field theories that I'm considering here. Now, it turns out that these coordinates are very explicit, but they don't make clear the true symmetries of the theory. So one can also characterize the coordinates on the space of conformal field theories a little bit differently in terms of a group coset. So in particular, it turns out that the G and B field are coordinates on O(n), n, the orthogonal group of signature n, n, divided by O(n) times O(n). Okay, just as a quick check, you can do some counting and check that the dimension of this moduli space is dimension n squared, as it should be if Gij is a symmetric n by n matrix and Bij is an anti-symmetric n by n matrix. Okay. So this is Narain's moduli space of free boson conformal field theories. And in the example that I'll discuss today, when I talk about averaging over this space of conformal field theories, this moduli space is the space I want to average over. So the next question is, what probability distribution should I take on this space? So the advantage here is that this moduli space is a homogeneous space. Yes?
There's a question again.
Sorry,
Please.
if you are summing over this space, which is basically integrating over G's and B's,
Exactly.
You are basically doing in target space some piece of gravity, because
Exactly. The way that I think about this is so for example, this expectation value is an integral over this moduli space of the free boson partition function as a function of the moduli. And I think about this as a piece of the full string theory path integral, but just one piece of it. I think it's fair to think about it that way. It is, in a sense, a gravitational path integral where I'm integrating over target space metric.
Right, but that means that in ADS-CFT, what you are doing, you're integrating over boundary conditions where the metric lives of target space metric. So you are doing something really drastic in terms of original ADS-CFT.
Well, I'm not integrating over the boundary metric in ADS-CFT. In this picture, the boundary metric would be the world sheet metric of this 2D CFT. I'm integrating over a target space metric, but not over a world sheet metric. So the world sheet metric, the boundary metric is kept fixed, but the target space metric, which I think of as parameterizing a set of couplings in my space of conformal field theories, is the thing that's being integrated over. So I'd say this is really quite in the usual spirit of ADS-CFT. For example, this partition function will be a function of the metric of my boundary. So in particular, it'll be a function of the conformal structure of the boundary. And I'll see that very explicitly in a minute.
Alex, but when you say this is in the spirit, you still mean that you have a family of CFTs and you're integrating.
It's in the spirit of ADS-CFT in the sense that I am studying a theory of gravity in ADS with specified boundary conditions that include, for example, specifying the metric or the conformal structure of the boundary, but I am averaging over the couplings of my conformal field theory in the sense of this ensemble picture that I have tried to advocate.
Sorry.
What fixes the measure of that?
That's exactly what I'll talk about in a second, but it sounded like there was another question. So let me see if
actually I wanted to disagree, if I may, because from the point of ADS, the boundary conditions are put on the metric and dilaton or whatever. This is data. These are couplings from the point of view.
Indeed. So it is an integral over some of those couplings, which are usually fixed in the standard picture of ADS-CFT, and I am now allowing to vary, and I'm going to integrate over them. So it's an integral over an additional set of degrees of freedom that I usually don't integrate over an ADS-CFT.
Right. Now let's think from the point of the string theory on ADS side. So we have a string theory on ADS side, and these boundary conditions in that string theory on ADS 5 or whatever are initial data in a string theory over which we are now averaging. So from the point of string theory in target space, we are doing the gravity with the boundary conditions where we integrate our boundary conditions, which is in that sense is not allowed, because
it is I would say, oh, sorry, please continue.
Now, what I was saying is that from the point of gravity in target space, these boundary conditions are initial data. So we have to scatter some whatever particles in the target space. We need to put, like, I don't know, Astotic-Minkowski or ADS, we put something, and from the point of view of that string theory, on the left-hand side of ADS-CFT correspondence, this is not allowed trick.
Certainly, the theory that I'm studying is not string theory in ADS.
Yes, it's not string theory.
is-
That's what
Absolutely. It is absolutely not string theory in ADS, nor is it intended to be. It is intended to be a simpler theory of gravity that has the disadvantage that it is not an exact UV complete theory in the sense that it has a discrete spectrum and so forth, but has the advantage that it's going to be more or less exactly solvable. So the trade-off that I'm making is I am not studying string theory in the bulk, nor am I pretending to, but the advantage is that I'll get something that is at least from a certain point of view, exactly solvable.
Okay.
Great. Okay, so there's a question, I think it was Julian who asked, what is the probability distribution? Well, the reason why I wrote the moduli space of theories as a coset is that you can now see that it's a homogeneous space. You know, it's got O, N, comma, N isometries. And because of that, it has a unique probability distribution, right? What is that probability distribution? It's the square root of the determinant of the metric, where my metric is the unique left invariant metric on this homogeneous space. Okay, so it has a unique probability density, and remarkably, it also has a finite volume. Okay, so that means that I can interpret this, measure on this moduli space as a probability distribution. And in order for that to work, it's crucial that I need to remember about T-duality. So here on the left, I've quotiented out by O, N, and Z, which is the T-duality group for N-free bosons. And when you do that quotient to make sure that you're not double counting theories that are actually the same under T-duality, you get a space with finite volume. And the upshot is that I can compute the average of any observable. So here, what I'm doing is I'm imagining averaging over the space of conformal field theories of the partition function on an arbitrary Riemann surface. And the answer takes exactly the form that you would expect in a theory of gravity, in the sense that it takes the form of a sum over instantons, by which I mean a sum over Euclidean geometries in 3 dimensions, which fill in that boundary surface. So these are 3-dimensional manifolds whose boundary is equal to that surface. And in particular, the quantity that is going to be summed over is going to take the form of something that looks like a classical action plus a loop correction, and that's it. Now, this is very different from what you would expect in a more complicated theory of gravity. So among other things, in a more complicated theory of gravity, you would expect an infinite series of perturbative corrections to a classical action. But the theory that we're going to study is so simple. It's really a toy model where you can compute everything exactly. So in particular, in this picture, you might think of this as an exact holographic duality, because the bulk is one loop exact. So that means that you can compute all of the perturbative corrections around an arbitrary saddle point. And the Euclidean saddle points are simple enough that we can enumerate them exactly. So this would be an example of a theory where you can compute all of the instanton corrections and compute all of the perturbative corrections around each instanton and sum it up and get an answer that makes sense. Okay. And so that's, I don't want to go too much into the details, but I'll just tell you a little bit about what the proposed bulk theory looks like. Okay. So the first thing that we want to notice is that if you just look at this bulk theory that I've written here, you know, obviously this is a theory with a bunch of free bosons, so it has a huge amount of symmetry. In particular, it has a huge current algebra of symmetries, and it has specifically a U1 to the 2n current algebra worth of global symmetries. Now, from the CFT side, these are global symmetries. But as we all know, global symmetries on the boundary turn into gauge symmetries in the bulk. So that means that our bulk theory, we would expect, should look something like a Chern-Simons theory, and in particular, a U1 to the n Chern-Simons theory. Okay. So what would such a Chern-Simons theory look like? Well, let's just imagine taking a bulk geometry, which is some handle body. Okay, so here it's going to be some way of filling in a Riemann surface with some three-dimensional geometry, which I've sketched here. Okay, and let's just imagine trying to compute the U1 Chern-Simons partition function expanded around the trivial flat connection on this handle body. Okay. So if I was, so U1 Chern-Simons theory is a free theory, right? I mean, it has no coupling constants. You can just do it. It's some ratio of one loop determinants. Here you have a gauge boson determinant in the denominator. Then you've got a numerator that includes, for example, the Faddeev of Popov ghosts, and you can just go ahead and compute it. So there's a well-established technology for computing such one-loop determinants. The answer, of course, goes like something to the n, because I'm taking a theory of n perturbative fields. And what is the answer? Well, I've written the answer for you here. There's just a couple of details that I want to mention. So, for example, it includes the regularized volume of my three-dimensional bulk. You might ask, why does it include that volume? I didn't have an Einstein-Hilbert term in my action. I just have a bunch of Chern-Simons fields. Effectively, this is something that gets induced by one-loop effects. Okay. There's a couple different ways of thinking about it. You could think of it as an effective one-loop contribution to the cosmological constant, if you like, or you could just think about it as, you know, as something that appears when you study Chern-Simons theory at one loop. Okay. And then there's something that involves this geometry of the three-dimensional bulk, but it involves it in a very simple way. And in particular, you can write the answer in terms of the determinant of the Laplacian in 2D. So this is the determinant of the Laplacian on the boundary. So in particular, we have a bulk with a hyperbolic metric, and we have a boundary which has some specified conformal structure. And so you can compute the Laplacian with respect to that boundary metric. And at least in principle, although it's not something that's easy to do in practice, except in very specific settings, you could imagine computing the one-loop determinant. And it turns out to take exactly the form that I've written here. Okay. And omega is the period matrix of this Riemann surface. So all of these formulas are very fancy, but they're saying something really rather straightforward. In the language of conformal field theory, what does Chern-Simons theory do for a living? It computes conformal blocks, right? And a U1 Chern-Simons theory computes current algebra blocks for the U1 times U1 current algebra. Here, I really should have called this U1 to the 2n, actually. Right? It's a conformal block for the current algebra U1 to the 2n. Okay. And I'm actually using here some work by some people that I know may or may not be in the audience, but which was very helpful in trying to figure this out precisely. So that is what you might think the theory looks like perturbatively. But how does this compare to what you get when you average over the space of free bosons? So in particular, let's imagine computing this average over the space of free bosons. Here, M is going to be a coordinate on the space of CFTs, a coordinate on this moduli space. And it turns out that there's a mathematical trick, a mathematical tool that allows you to compute such integrals, known as the Sigel Way formula. And when we do this computation, it turns out you get an answer that looks very, very similar to what I got up above. Okay? So in particular, it involves something that looks like the determinant of the imaginary part of the period matrix divided by a determinant that you would use to compute the partition function of a bunch of free bosons. Okay, right? Because if you have a bunch of free bosons on the boundary and you were to compute the partition function, that would include, among other things, 1 over the square root of the determinant of your boundary Laplacian. And if you had n free bosons, you would have that to the nth power. The thing that's interesting is that when you do this Sigel Way formula to compute the average, you get that expression, but you get it summed over the modular group. Okay. So here, if you think of your boundary as a genus G surface, this modular group is just the group of large diffeomorphisms or large conformal transformations acting on your Riemann surface at the boundary. Okay. This is the set of large diffeomorphisms that permute the various boundary cycles of your boundary surface in a way that is consistent with the symplectic pairing between cycles. Okay. Good. But this, it turns out, has a rather a beautiful interpretation, which is that this sum over the modular group can be interpreted as a sum over bulk geometries. How do we see that? Well, let's just imagine a prototypical bulk geometry that, such as the one I was thinking about on the previous slide, that might contribute to this sum. So how do you describe such a bulk geometry? Well, your boundary is some Riemann surface. I've taken it to be a genus 2 surface here. And the way that you would specify a bulk is by choosing a pair of cycles on this boundary, and then taking your bulk to be the handle body that fills them in. Okay. So here I've drawn such a handle body, such a 3-manifold. But now, because the bulk requires a choice of cycles, there are going to be many such bulk configurations, which correspond to different choices of cycles that are contractible in this 3-manifold. And this modular group just permutes your choice of cycles that are contractible. And so, in fact, this modular group labels different handle bodies in the bulk. It labels different bulk geometries. Okay. And so this sum is, in fact, interpreted as a sum over handle bodies, as a sum over geometries. So our conclusion then is that this simple average over a space of conformal field theories can be interpreted as a sum over geometries, that's this guy here, times sum of something that you would think of as a classical action plus a one-loop contribution. Okay. And in fact, sums of this sort have a name. They're called Eisenstein series. And I'd like to spend the next few minutes trying to unpack them in a little bit more detail. Maybe before I do so, I should just pause and see if there's any questions on that.
Just one small
yes.
clarification. The small g here is the genus of the surface, right? Or
okay. Yeah. So for example, this would be a genus 2 surface. Okay. Great. Any other questions?
I don't see any. I think. Go ahead.
Great. So let's try and do a simple version of this calculation. Okay. So let's take my torus to be the boundary. So, or sorry, let's take my boundary to be the torus. Okay. The torus partition function of a CFT computes the spectrum of the theory, right? Z of tau, or let's call it beta and theta, would be the integral d beta e to the minus beta e times the sum over j of e to the I theta j. Oops, something just happened to my slides here. Oh, sorry about this. Okay. E to the I theta j. Sorry, it turns out I can't draw on that corner without it taking over the rest of my screen. Okay. So I'll redraw that. So the partition function on the torus would be the integral d beta e to the minus beta e sum over j e to the I theta j times the density of states. if J is the spin and E is the energy, or in the CFT language, the scaling dimension of an operator. And here the tau parameter would be given by the usual form in terms of the inverse temperature and angular potential. Okay. So how would we go ahead and compute the average of the torus partition function? Well, this now would be the sum over modular transformations of the torus, which on the last slide, I wrote as a symplectic group for arbitrary genus, but on the torus, this is just a sum over SL2Z. If you go through the details, it turns out to be a sum over SL2Z mod Z, which you can write as a sum over pairs of coprime integers. Where here, a pair of coprime integers you can think of as just the lower row of some SL2Z matrix. Okay. And from the gravity side, you can think of the sum over C and D as a sum over Euclidean geometries with some boundary torus where C and D label which cycle is contractible in the bulk. So if I call T and phi my two cycles of the boundary torus, then we're summing over which cycle is contractible. So you can go ahead and extract from that the density of states. It turns out it's rather simple. Here I've written down the density of states at spin 0. The density of states at finite spin is not much more complicated. And what do you get? You get a delta function at 0. That's the vacuum state. And you get something that goes like delta to the central charge. Okay. That is the analog of Cardy's formula in this set of conformal field theories, which is to say that is the analog of black hole entropy. Okay. The heavy states in the theory are the things that come from Euclidean saddle points. They are the things that are counted by Euclidean saddle points where the time circle is contractible. Now, what is a Euclidean saddle point where the time circle is contractible? It's a black hole, right? It's the Euclidean BTZ black hole. And so the high energy density of states is representing the analog of the black hole states in this theory of gravity. Okay. Now, this is a very simple theory of gravity that differs from Einstein gravity. So in Einstein gravity, you would expect E to the square root of central charge times delta. That's E to the area of the black hole in Planck units. Now, in this simple theory of gravity, that exponential is being replaced by a power law. Okay, so this is a little bit like a theory of gravity where the Bekenstein-Hawking entropy is not proportional to the area of a black hole, but the log of the area of a black hole. Okay. Right. Because this formula here goes like E to the central charge times log delta, okay, instead of delta to the 1/2. Okay. So this is something like a simple theory of gravity with a paucity of black hole states. Yes, was there a question? Maybe that was Julian.
Just a quick question, because this might be good point to ask that question, which may be more general. But so here, the density of states, you've shown us the result of this average computation. Do you know how to compare it to the density of states of a single member of the ensemble that you've averaged over?
So a single member of the ensemble will have the same asymptotic behavior for the high energy density of states, but it will differ in the details. So in particular, in an individual member of the ensemble, this density of states, of course, will be a sum of delta functions. And what happens is when you average, that sum over delta functions gets smoothed out. Now, of course, this high energy density of states is a consequence of modular invariance. So it'll be true in any individual instance of the theory. But you would only, so for example, the density of states, if you coarse grained, that is to say, if you averaged over states in some window, it would go like delta to the n, but it would be, it would be a sum of delta functions. In the same way that the standard Cardy formula in any conformal field theory is approximating a sum of delta functions at high energy by some smooth distribution. Yeah.
Do you know what and how strongly this formula that you write depends on your procedure for averaging? I mean, you've shown us a very
Good. It does depend on the procedure for averaging. I have comments I could make about how to compute it for more general stuff. I'll do that at the end if I have time. I'll write down a formula.
Yeah, I'll remind you.
Sorry, Alex,
Great.
one more question.
Yep.
The formula you wrote here is valid, what, at large delta or delta much larger than 1?
No, this
or-
is an exact formula. I've computed everything exactly, except I didn't feel like writing down the number because it's got like zeta functions and stuff like that. This is an exact formula for the average density of states. It also matches the average density of states in a particular CFT at high energies.
I see. So
This
so
is an
the-
exact expression. And I'll write down, yeah.
So the inverse Laplace transform that you have to do to go from the partition function to the density of states, you can do it exactly, and you land on this.
Yep. Yep. Good. That's important to mention. Everything, this is a theory of gravity where I can do everything exactly. The price of being able to do everything exactly is that it does not have a discrete density of states. Okay. It's only in a super fancy theory of gravity that I can get a discrete density of states, which would be the discrete black hole microscopics. But I sacrifice my ability to get a discrete density of states for the ability to compute everything exactly. Let me give you another example. This is probably a more non-trivial example. Let's please, no such thing. Well, maybe let's go ahead and see.
I think you basically gave the answer, just to be sure. So this number in front of the delta to the n term, in principle, you actually know it. You just didn't want to bother us.
Oh, yeah. I was just lazy. I'm a very lazy person. Yeah, so there's some number here that I know. Yeah. I'll write down the analog of this number on the next slide. So let's do something more complicated. Let's study not the density of states. Let's study the statistics of the density of states. Because even though I can't do things like get a discrete spectrum, I could still compute things like the 2-point function of the spectrum or the higher point function of the spectrum. So this would tell me, for example, about things like level repulsion in the spectrum, which is what you would expect if you had a chaotic theory. It will also tell me about things like the spectral form factor, as we'll describe in a second. Okay. So how do you do the sum? Well, it's almost exactly the same thing that I wrote down on the other side. It's a sum over that modular group, except now instead of SL2Z, I have a sum over SP4Z. Okay. And I've written that as a sum over pairs of matrices C and D, which you should think of as making up the lower row of some SP4Z matrix. Okay. And just as on the previous, so here, again, I think about this as a gravitational path integral, where I have a sum over geometries whose boundary is a pair of toruses, or maybe it's a pair of tori, I don't know. And so just as on the previous slide, my boundary was a single torus, and my choice of C and D labeled which cycles are contractible. Now, again, I have a pair of boundary tori, and my choice of C and D labels which cycles are contractible in the bulk. Okay. Now, some of these geometries are going to be things that are disconnected in the bulk. So for example, there's this one that I've called thermal ADS union thermal ADS. What is thermal ADS? It's my name for the Euclidean geometry where the spatial cycle is contractible, okay? Because that's the Euclidean geometry you would use to compute thermal correlation functions in ADS3. And then there's another one, which would be BTZ union BTZ. That would be one where it's the time cycle that's contractible in the bulk. But then more interestingly, there are going to be other contributions which correspond to connected wormholes. So for example, if you look at this pair of matrices here, what is that telling us? That's telling us that T1 plus T2 and phi1 minus phi2 are contractible. Okay. What does that mean? That means that phi1 is equal to phi2 and T1 is equal to minus T2. Here, T and phi label the different cycles on the boundary torus. And so you can see that this corresponds to some connected contribution, which schematically would be of the form of torus times an interval. But there's a question. Yeah.
Sorry, question.
Yes. Thank you.
Does it play a role whether your wormholes are traversable or not? Is this of any relevance?
This is Euclidean signature. So
okay.
the notion of traversable is not something I can say anything about. As you know, there's a big difference between Euclidean wormholes and Lorentzian wormholes. Lorentzian wormholes are fairly innocuous. A black hole is a Lorentzian wormhole in a sense. Euclidean wormholes are different, and the notion of traversability is not something I can say anything about.
So this leads to my second question. I mean, there's wormholes play this important role in things related to ERs, EPR, and things like that.
Yeah.
But this is outside.
This is distinct. This is distinct. Yeah.
Okay.
Yeah. I don't have too much. I don't have too much to say about Lorentzian signature, but we can get there if you like. Okay.
But if you analytically continue an eternal traversable wormhole to Euclidean, you would get something that looks exactly like this.
I guess that's right. Yeah, non-traversable, you would get something connected. Traversable, you would get something like this. I guess that's right. I haven't really thought about it, but I'd be happy to discuss that more if you guys want. But let me just go ahead and use this to get an answer. Okay. Okay, my tablet is getting tired. This formula is too complicated for my tablet to display, apparently. Let's give this another try. Okay. So, God, can you see that? It's looking very fuzzy. Okay, it's looking very fuzzy. Maybe if we give my tablet a minute to calm down and think about what it's done, it'll be able to display this formula. What's that?
This is what happens when you average.
This is what happens when you average, exactly. Okay, so what am I writing down here? What I'm writing down is, oh my God, I can even write on. Okay, what I'm writing down here is an exact expression for the density of states. Okay, everything is disappearing here. This is very weird. Okay, you know what I'm going to try and do? Let's see. That's super annoying. Oh, there we go. Can you guys see that?
We had it for a second. Oh yeah.
It's the same thing.
Great. So for example, we can compute the exact 2-point correlation function. Okay. And in fact, it has a very beautiful interpretation. So this is the thing that captures the spectral statistics of the theory. Okay. This is what I described in my paper with Scott over the summer. Really, what were we doing? To some large extent, we were unpacking papers from 50 years ago by Maas, the mathematician. But what does this result have as an interpretation? Well, I'm computing the correlation function, and in particular here, I'm writing down the connected part of the 2-point correlation function for the density of states in this ensemble of theories. And what form does it take? Well, there's two terms. There's a bunch of delta functions that arise when one of the dimensions is a rational number times another dimension. Okay. Now, why does that happen? That happens because in free boson CFTs, the primary states, and here I'm writing down the density of states of primary operators, are all things of the form e to the I kx. Okay. And so if you have a primary state of one dimension, then you're assured of having a primary state of another dimension that's a rational multiple of this. Okay, so that's where that delta function is coming in. That's not the interesting part. The interesting part is the stuff that's not a delta function. And if we were in a random matrix theory, this is what would be given by the sign kernel. Okay, this thing that describes the level repulsion, for example, of states of eigenvalues of random matrices. But interestingly, this is neither Poisson nor random matrix statistics. It was mentioned to me that the appropriate name for something that's between Poisson statistics. So Poisson statistics are what are expected for integrable systems. Random matrix statistics are what you expect for a chaotic theory. It was suggested to me that the appropriate name for statistics that lie between Poisson and random matrix would be Merman statistics. because of course, random matrix statistics were devised by Wigner and Dyson, who were humans. Poisson obviously was a fish. And so anything that's intermediate between Poisson and random matrix statistics would be merman statistics. Okay, this is in Switzerland. Are you in the French speaking part of Switzerland or the German speaking part of Switzerland? So I can tell if people got that joke. Okay. I see Julian looks very upset with me. So I can assume that at least some people got that joke. Okay. What does this? That's a good one. That's why this is what jokes like that are what helped me get up in the morning. Good. So it's easier to draw a picture to summarize this result.
Can we go back to the joke?
Yes, please.
I have a question. Yeah.
Again, there's a number. I know the number. I'm not going to tell you the number because it's complicated.
I don't want to know the number, but were you? I mean, how did you deal with symmetries? Like, I mean, probably this theory has a high degree of symmetries, like a bunch of.
Yes. So for example, let me. Oh, sorry, I can't quite hear you.
If you want some fish or a meat, you have to go to one symmetry restricted sector, right? It will not be Poisson if you have more than one of these symmetry sectors. You need to go to like a block in which all of the symmetries are fixed in some sense. Did you do that?
Yeah, I mean, I will say that well, I mean, I can tell you what I did, which is that here I'm working in a sector where I'm looking at the correlation function between scalars. We could look in different sectors if you like. Obviously, these theories have tons of symmetry, which I think is why you're not getting random matrix statistics or anything like it. Yeah, we can talk more about the interpretation if you like. I mean, like these are not here. Maybe it'll be helpful if I instead show the spectral form factor.
Let's take an integrable spin chain, which we know should have Poisson statistics. But if you just diagonalize its spectrum and look at the statistics, you won't find either Poisson nor Wigner-Dyson. And the reason is that the reason is that you need to restrict to a specific symmetry sector. So I'm wondering if that is also the case here, since it's possible.
It's possible. It's possible. I'd be happy to talk about it. I mean, as I mentioned, you know, this is not random matrix statistics. I did not see a way of getting this to be exactly Poisson statistics. You know, actually, if you look in this other paper, what we did in that paper is we went to a fixed charge sector, which would be, so of course, this theory has a bunch of U1 currents, so you can go to a sector of fixed U1 charge, and you can write down the density of states in that sector. You know, there's a formula that did not, as far as I know, look like Poisson statistics. But I'd be happy to talk more about that. Yeah. So I think the answer of what you're looking for might be in that paper.
Alex, you have 5 minutes left.
Great. Okay. So you can write down the spectral form factor. What is the point of the spectral form factor? Well, the spectral form factor is this thing that characterizes the spectral statistics by looking in Lorentzian signature. And in particular, a general consequence of unitarity is that if you go to late time for the spectral form factor, you're going to approach a constant. And in any theory of gravity that people study, one of the sort of main challenges is to see if you can understand the discreteness of the spectrum by thinking about a sum over geometries. And what we're seeing here is that the spectral form factor of this ensemble of CFTs that we've studied, it does indeed have a plateau. Okay, you know, it approaches a constant at late times. And that constant is exactly Z of 2 beta, which is the expected value of the plateau. So I find this very heartening because what it means is that we have a theory of gravity that is smart enough to know about the discreteness of the spectrum, even though the spectrum itself is not discrete. in the sense that the density of states is not a sum of delta functions, but nevertheless, the correlation functions of the average density of states have the expected properties that one would expect for a theory with a discrete spectrum. Okay. Now, in an actual theory with a discrete spectrum, this plateau would be something that arises on average. You know, it would be some sort of, you would have some sort of very rapidly varying behavior for the spectral form factor at late times that only averages out to a constant. Here in this ensemble, we get exactly that constant. Okay. So I think this is important as an example where a sum over geometries has reproduced the discreteness of the microstates in the theory through the spectral form factor, although not through the spectrum itself. Good. So let me, in the interest of time, I'll just go very briefly through the last few things I wanted to say, which is that you can talk about, finite n corrections and what they look like, because everything can be computed exactly. There's one interesting distinction between the annealed and quenched free energies of the theory that I think is worth talking about if anyone is interested. I think there's also some interesting things we could say about how unitary is restored as we go from some probability distribution to an individual CFT. In particular, one can write down the partition function of an exact system of n free bosons, and you can write it as given by its averaged value plus a bunch of corrections. And here I've written down those corrections in terms of some Eisenstein series, some cusp forms and stuff like that, which you can think of as the deviations from the average that would end up restoring unitarity. So I think this is something that would be great to look at in the future. I think it is these terms over here that are the magical things that essentially cancel out the contribution of the wormholes, or at least we should say correct the contribution of the wormholes to give you to restore factorization in Euclidean signature. Okay. And so I think, I've written down the answers here in a very formal way. I think there's probably a lot to be learned from how exactly they restore unitarity. Okay. So as usual, I have an infinite amount that I could say about speculating about what to do in the future. Maybe I will just end with a couple of comments about more complicated theories of gravity. So the real drawback of this example that I described today is that the Narain theories are simple, but in some sense they are too simple. The reason I can write down exact formulas is that they're really basically cusped at the edge of being solvable integrable theories. In 2D CFT language, a theory with central charge less than the number of currents is a rational theory with a finite number of primary states. A theory with a central charge bigger than the number of currents is a genuinely chaotic theory with an exponentially growing number of primary states, according to Cardy's formula. These Narain theories, I think of things that are kind of perched at the edge between integrable and chaotic in the sense that they have a central charge equal to the number of currents. So you have an infinite number of primary operators in the theory, but the density of states grows polynomially instead of exponentially. Okay. What we really want are more chaotic examples. Okay. And optimistically, I would think that pure general relativity should be an average over all conformal field theories. That is to say, general relativity, as defined by a Euclidean path integral over metrics with a specified boundary, weighted by the Einstein-Hilbert action, appropriately regularized, should be equal to some kind of average over the space of conformal field theories. And here, I think there's a natural guess for what the measure should be. But I don't have anything terribly insightful to say about how to compute this average exactly, except to say that if this statement is true, it has dramatic consequences for our understanding of the space of conformal field theories. Okay, and I think this is something that's worth mulling over for a second. So one interesting feature of pure three-dimensional gravity in anti-de Sitter space is that it has a huge gap. You know, the first excited state of the theory is the BTC black hole. In the scalar sector, the first excited state has dimension equal to the central charge over 12. Okay. Now, I know of no conformal field theory which has a gap bigger than 2, right? I don't know any 2D CFT where the lightest primary operator has dimension bigger than 2. Okay. And so, in general, it's been a very sort of interesting challenge to understand how to construct even one example of a conformal field theory where the lightest primary operator has dimension of order the central charge. But if this conjecture is correct, not only do such CFTs exist, but they are typical, right? Not only is there some large central charge CFT out there with dimension equal to the central charge over 12, but almost every CFT will have that property, where I say almost every in the sense of probability theory with this measure. Okay. There's a couple other things that I think are a little bit confusing about this picture. So for example, one might guess that the space of conformal field theories has the property that the central charge takes discrete values. Okay, so probably what that means is that in order for a formula like this to be true, I should average over the central charge as well and work in some ensemble where not the central charge is fixed, but something else, you know, perhaps some grand canonical ensemble or something like that. I don't have too much terribly quantitative to say about that right now, but maybe I'll end, and this time when I say I'll end, I'll really end with the $64,000 question. Okay, what is that in Swiss francs? What is the, is it CHF? Is that the Swiss franc thing? I don't remember.
Less than 10 years ago.
Okay.
US dollars is like almost 60.
Yeah, okay. I don't know.
15,000.
Okay, what's the big question? Where does ensemble averaging come from? And if you ask me what I secretly believe the following. So when we talk about averaging in gravity, we could talk about ensemble averaging over a space of CFTs, but in fact, there's a much simpler and much more conventional averaging that we do, which is when we coarse grain over black hole microstates to get a geometry. So in particular, if you have some UV complete theory of quantum gravity, then you've got a bunch of black hole microstates in that theory. And when you coarse grain over them, when you average over those states, you're going to get some geometry emerging. Okay. So you could certainly imagine that you have a geometry of, you have some set of black hole microstates that when you coarse grain over them gives you a geometry which has some ADS near horizon region. And of course, these low dimensional theories of gravity that we study, things like JT gravity or even ADS3 gravity, those are theories that describe the near horizon dynamics of black holes. Okay. So I think what I would guess is that the ensemble averaging that we have discovered is in fact just a remnant of this coarse graining procedure. In particular, what I want to imagine doing is starting with an ensemble of black hole microstates in some UV complete higher dimensional theory of gravity. And then I want to imagine it dimensionally reducing down to 2 dimensions or 3 dimensions and taking a near horizon limit where you throw away the asymptotic behavior. And then that averaging over states in an individual theory should become an average over theories in the lower dimensional perspective. And so what I really think is that this ensemble averaging picture is a kind of remnant. It's a sort of echo of this coarse graining procedure over black hole microstates that appears in higher dimensions. Okay. I have some few ideas about how to make this precise. I'd be delighted to talk about them. But I'll save that for the question time or some discussion time, since I think I'm out of time. So I'll just thank everyone for their questions and their patience.